Okay, what's up, everybody? 10.4 today. We're going to talk about something known as the integral test. All right, let's go ahead and let's just dive right into it. So, the integral test says if f is positive, continuous, and decreasing, and that's something that's going to be important for us. For x is greater than or equal to 1, okay, and a sub n equals f sub n, then we have this rule here that we're going to turn the summation into some sort of improper integral, all right? And then, so what happens is if your integral is going to converge, then your series will, and if your integral diverges, then so will your series. All right. Couple of things to note as we go through this. Okay, this does not mean that the series converges to the value of the integral. Okay, just know that. So whatever the integral converges to, if it does, doesn't necessarily mean that the series will. And the one other thing is when we talk about increasing and decreasing, okay, the function that you are trying to take the integral of, it just has to be decreasing at some point in time for k being greater than or equal to 1. All right, let's go ahead and let's take a look at our first example here, shall we? All right, it says determine if the following series converges or diverges, justify your answer. Well, you're not always going to be provided with a graph, so let's see how I can get it to show that the series or here that the function itself is going to be decreasing, continuous, and positive. First thing that I'm going to do is I'm going to rewrite this thing as an improper integral. So let me go ahead and do this. So this is going to be from 1 to infinity, n over n squared plus 1, and then, no, not n, excuse me, replace n with x over x squared plus 1, and then dx. Okay, now if I take a look at this function, I know that if I try and find the limit of that function towards infinity, the limit as x approaches infinity, okay, of x over x squared plus 1, I can see that that is going to equal to 0. So thus, at some point in time, it has to be decreasing. Okay, so that is a little bit of a justification that lets us know that we know it's decreasing. If you start to plug in values of x or even n back into the original, we do know that it's going to be positive, and there looks like from 1 to infinity that there's not going to be any kind of discontinuity along the way. So we definitely know that it is decreasing, positive, and continuous. All right, let's go ahead and let's continue. We need to turn our improper integral into a proper integral. So we're going to do the limit as, let's see, as b approaches infinity of 1 to b. And then I'm going to have x over x squared plus 1 dx. Let's go ahead and let's do our integration. So I'm going to do it off to the side here. That looks like that's going to be a u sub u equals x squared plus 1. I'm just going to go through this because this is not new. And as I'm working through this, 1/2 du equals x dx, and we can see that that works out perfect for us. Okay, that gets rid of this part right there. So I am now going to go ahead and I'm just going to do the integration so I don't have to u sub there with the b's and everything. So this is going to be 1/2 the integral, and that's just going to be 1 over u, and we know that is 1/2. And that is going to be times the natural log of the absolute value of u, and then I'm going to go ahead and I'm going to do 1/2 times the natural log of, and I don't need absolute value brackets on this one because it's just going to be x squared plus 1, so it'll always be positive. So I know that that is the integral of the x over x squared plus 1. So now I should have the 1/2, or no, sorry. I should have the limit as b approaches infinity of 1/2. And then I'm going to do here natural log of, let's see, x squared plus 1. And that is going to be from 1 to b. And then this should be the limit as b approaches infinity of the natural log of b squared plus 1. Okay, minus the natural log of 2 when I plug in. And then, oh, and don't forget, and I'll sneak it in at the end. I'm just going to put times the 1/2 there. I just don't want to erase. So I should be good there. And then so that this should be 1/2 times, look like that's infinity minus the natural log of 2. That is not an indeterminate form. Okay, this is just equal to divergent. All right, so let's go ahead with our write-up here. We would say, since n over n squared plus 1 is positive, continuous, decreasing, and the integral from 1 to infinity of x over x squared plus 1 dx diverges. Therefore, sigma n equals 1. It's a long write-up. From the integral of n over n squared plus 1 also diverges by the integral test. All right, number 2. Okay, so if I do the limit for this one, the limit as n approaches infinity of 1 over n squared plus 1, you can see that that equals 0. So we know that somewhere along the lines, this thing is going to be decreasing. You should be able to just mentally plug in numbers starting at 1 going to infinity, knowing that the whole thing is going to be positive for anything n greater than or equal to 1. And we also know that it will always be continuous. There's no discontinuities in there for n being 1 or more. Okay, so let's go ahead and let's see how this thing is going to play. Looks like we're going to use the integral test. So I think the first thing that I'm going to do is I'm going to write this as an integral. And I am going to change all of my n's to x's. Okay, and that's going to be dx. And now I'm going to go ahead and I'm going to take this improper integral and I'm going to write it as a proper integral. The limit as b approaches infinity of 1 over 1 plus x squared dx. Hopefully you understand why I wrote it like that, because you should recognize this to be something right there. All right, so that is, yes, that's right, arctan. Okay, so this is the limit as b approaches infinity of arctan of x from 1 to b. So we've got the limit as b approaches infinity of arctan of b minus arctan of 1. All right, so arctan approaching infinity, that is pi over 2. Subtract arctan of 1 is pi over 4. And that's going to be 2 pi over 4 minus pi over 4, which is going to be pi over 4. So it converges to pi over 4, okay? So you cannot say that the original series converges to pi over 4. You can just say that it converges, okay? So we would say since, I guess I'll pick like a nicer color here, since 1 over n squared plus 1 is positive. We know it's positive because if you plug in values for n starting at 1 going to infinity, you get all positive numbers. Continuous. There are no points of discontinuity starting at n values of 1 going all the way to infinity. Decreasing. We know it's decreasing because we did this part right here where we wrote like a limit statement. So that lets me know that that thing is decreasing. We can see it's decreasing in the picture, but you're not always going to be given a picture. Continuous, decreasing, and the integral from 1 to infinity of 1 over x squared plus 1 converges. Therefore, summation, oh goodness, that's an ugly summation. Summation, oh my god, that's just as bad. N equals 1 to infinity of 1 over n squared plus 1 also converges by the integral test. Letter C. Okay. Well, let's see. Is it going to be decreasing? Let's just write a quick limit statement here. Okay, this would be the limit as n approaches infinity. I think I'll do n over e to the n squared. Okay, and you can see that the top is a poly and the bottom is an exponential, and we know that exponentials are going to grow faster, so therefore this does equal 0, so therefore we know that that thing is decreasing at some point in time, okay, along the way. Now, if you plug in values of 1 going to infinity for n, you'll see that everything is positive and it's also continuous. So right there, those three things, we're good to go. All right, so let's go ahead, and I think what I'm going to do is I'm going to go here with 1 to infinity, x e to the negative x squared, okay, and then that's dx. Change it to a proper integration, incorporating limits. B approaches infinity of 1 to b of x e to the negative x squared dx. Looks like this one is going to be a u sub. U equals negative x squared. So I know that du equals negative 2x dx. And then I'm going to get negative 1/2 du equals x dx. Looks like I took care of that. So if I do the integration off to the side, that's going to be negative 1/2. And then that is going to be e to the u du. So this is negative 1/2 e to the u. And then this is negative 1/2 e to the negative x squared. And that is the integration for that. So now I'll go ahead and I will plug in over here, and I will get the limit as b approaches infinity of 1 to b. Oh, no. The limit as b approaches infinity, negative 1/2. And then I am going to do e to the negative x squared, evaluated from 1 to b. So we could go ahead, and you know what I'm actually going to do? Watch this. Negative 1/2, the limit as b approaches infinity. Move that negative 1/2 on the outside because I can. And this is going to become 1 over e to the b squared, subtract 1 over e. That's me dropping the x squared down to the denominator to get it to be a positive exponent. Okay, and then I'm going to go ahead and I'm going to simplify this. So this is negative 1/2, plug in infinity. So this part right there gets bigger, so the fractions go into 0 for that one. So that's going to be 0 minus 1 over e. So it looks like this is actually equal to something finite, which is going to be 1 over 2e. So therefore, it converges. So then therefore, the series converges. So as your statement, I guess I'll just go to one more here. Since n e to the negative n squared is positive, continuous, decreasing, and the integral from 1 to infinity of 1 over x squared plus 1 dx converges. Therefore, summation n equals 1 to infinity, 1 over n squared plus 1 also converges by the integral test. smiley face. And that is it. 10.4, integral test. Mr. Miller's out.